So this is part 4 of our review of chapter 17, orthogonal matrices and Gram-Schmidt, and we already discussed about Gram-Schmidt in the previous part. So let's discuss the last one, which is the vectorization of the orthogonal matrices. So let me write this down first. So A equals QR. So let me talk about the concept or what we are doing here. So when we talk about, we start with the ABC, which is just the set of individual vectors, and we want to get to Q1, Q2, Q3, the orthonormal. So there must be some kind of matrix which is just a bunch of number that brings us from Q1, Q2, Q3 that acts on this set of matrix and then brings us to ABC, or the other way around, that acts on set of ABC and then brings us to Q1, Q2, Q3. And we already have seen this before in the earlier lecture where we talk about A equals LU, so the lower triangular times the upper triangular. So in this case I think we are doing some factorization that brings us from the matrix A into the row reduced echelon form, or something about the elimination. So this is also the same thing, that there must be some vector set of vectors or a matrix that acts on A, and then that gives us the R, and then or also if we have some matrix on R and then brings us to A. So that is similar to what we're doing here. So let me delete something first to give me some space. I'll just delete this one because it is enough to discuss about this till the end. There's one thing that I would like to note, that let's observe that when we compute capital A, capital B, and capital C, the capital A is only a vector of A, whereas capital B is a vector of that B and A. So that there are two variables play a part here, where in a capital C there are three variables that play a part. So the big A and big B, and that's it. Similarly to the second formula that we have here, the first one we don't depend on the vector B or vector C, but in the Q2 we depend on the B and Q1, and in the Q3 we depend on a lot of factor here. So what does that mean? So that means if I have this ABC, which is my initial A, and equal to Q1, Q2, Q3, so these are all column vector. Okay, so the A is coming from the Q1, but it's only multiplied by something. So the Q2 and Q3 in this case, there is no Q2, Q3, there is 0 of them. Similarly here, there are 0 of any like B or Q2. There is no anything that mentioned about this component when we compute the capital A. So therefore, we only multiply by some component here in the initial component, and the rest of them are 0 because, again, when you multiply them, this is just like the coefficient of Q1, and 0 is coefficient of Q2, 0 coefficient of Q3. Well, similarly, on getting the B, it begins to have these two factor here, because we also see that Q1 is play a part, and then the B itself will play a part, the Q2 itself, sorry, I mean, and then the Q3 doesn't play any part here, so it is 0. And similarly the same thing here. So X is some number that we will soon figure out, but the thing is they form this upper triangular matrix. So this, in the book, we gave it a name R, and this axis, it has this format of Q1 transpose A, Q1 transpose B, Q2 transpose B, Q1 transpose C, Q2 transpose C, and Q3 transpose C. 0, 0, 0, 0. Let me write this down. So that's all that I can explain to you about A equal Q multiplied by R. One last thing that I want to mention here is, if you see it this way, so A is actually the component of A that lives in Q1. So A and Q1 lives in a single line, and the B, it's composed of two components. So the component of B that lives in the Q1 and the component B that lives in the Q2. So that's the reason why B is kind of looks like this. So this is like Q1 or A, but B is actually has two components, so those that live in the Q2, that the subset that we want, and the one that lives in the Q1. So B has those two components, while C have these three components, that the C component that lives in the Q1, C component lives in the Q2, and the Q3. So that's it, folks. Bye bye.